My name is George Romanic. I come from McGill University, and I am not in Faculty of Engineering. I am in the Department of Atmospheric and Oceanic Sciences. But the work here is mostly done by Professor Matthias Bezabek from Faculty of Engineering, and he is exceptional PhD student now from Berlin. So what I'm going to talk about is nonlinear dynamic response of structures under stochastically simulated downburst winds. So in Canada we also have a lot of downbursts. These are data that came from the Northern Tornado database. We have much more actually downbursts than tornadoes. We get approximately 100 tornadoes per year, but at least 2 times more than that of downbursts. And you can see that forget about all colors, this is from different papers. Downbursts are red, and you can see they are mostly blue, so they are along the southern border of Canada, mostly here in Ontario and around Toronto and so on. So this is a universal slide that I use to explain every possible wind system in Canada. In earlier presentation, as I said, tornadoes are the nastiest per event. They create the biggest damage per event. But when we accumulate over years, then on average, convective storms red is Ontario and blue is Quebec. So convective storms, downbursts, create most damage in Quebec and Ontario in Canada. So they are worth investigating, and that's what we did in this study. Now, we stochastically simulated downburst time series. Downburst wind speed can be clearly decomposed as the mean, that is function of height and time, and turbulence fluctuations. Now, mean, that is function of height and time, is decomposed as one function that is only function of height and another function that is only function of time, classical method. For the height dependency of the mean wind, we used famous Wood model, where you need to insert the peak velocity that is usually at a height of between 80 and 150 meters above the ground, and then there is this delta, that's the value where the profile reaches 50% of the peak. So the height where the wind speed is 40 meters per second in this case, or in simple words I can just describe it here. So this is peak, this is delta, 400 meters in this case. This is also important to remember because later we parametrically analyzed the influence of the change of the height of the maximum velocity on the structural responses. So there was a parametric study associated with that. Now the time function, we used the approach by Chen and Ledgeford in their excellent paper on cantilever structures affected by downburst winds. And here they said that combined wind speed, UC, is radial wind speed, that is function of time produced by the downdraft, by downburst, and translational velocity of the cloud. So here we have actually radial velocity as a function of distance, and translation is added. So you can see that at r equals 0, we don't get velocity that is equal to 0. And the time function, this is all from Chen and Ledgeford. Time function is determined by normalizing this UC, but as a function of time now. So you have a fixed point and a downburst is translating, and you measure what you get at that fixed point. Now I would like to say that in a paper that we are publishing now, we actually use different time function. We use time function from Roncallo and Solari, but I wanted to be consistent here with the abstract that we submitted, so we left what we used in abstract for this conference. Now, fluctuations are a uniformly modulated process. That means that actual fluctuations are fluctuations that have a unit standard deviation and 0 mean, and then they are modulated by basically turbulence intensity. And this was also tested what would be turbulence density between 5% and I think 35%. So this constant turbulence density means that A is proportional to U average. And then we use a typical method of Rice, 1944, 1954. When I read papers by Rice, I didn't understand anything, but like paper is 100 pages, mathematics is over the top. So fortunately, Shinzuka and Deodatis lower down this whole mathematics for us mortals and put it in the form of a nice equation. So everybody is using this same technique, except we don't code it this way, we code it using fast Fourier transforms. And as I said, fluctuations here are generated at different heights, J, sorry. So you have to have also coherence function, and we use Davenport's coherence function here. Very standard. Okay, so that's how we generate the downburst. Now, how about building? I come from atmospheric sciences, but I will present this structural part as well, okay? Now, this is a 2D finite element model building, so it's already simplification from 3D building. And what they did is they determined mass, stiffness, and damping. They put it in a like 1D model, concentrated mass shear model. And now, how did they approximate 2D to be 1D? Well, they have 2D finite element model. They do model analysis. They obtain mass and stiffness of each story. I'll tell you now what is the size of the building. But at any rate, to carry out finite element method for all possible realizations of our downburst is too expensive. So they did it for one case, the so-called nonlinear static pushover analysis, where you statically apply some load and you calculate responses. And they ran FEM, and they then did the same for this simplified model, and they fine-tuned coefficients in the simplified model to reach finite element model. When that was the case, you carry out nonlinear dynamic analysis, then you subject everything to downburst. This building was, Professor Bezer's student designed this building to be in Toronto with to sustain gust of return period of 50 years. It's an 18-story building, 62 meters high, 3-point-something meter is the difference between different stories, okay? And here are some of the results, building responses. So first, x-axis is time, and this is ductility. So this is response divided by the yield response for a given floor, and here is floor 10 because it was critical floor. So you can see as the time is progressing, so when this exceeds 1, you are in nonlinear, non-elastic range. So here you are in elastic range, and then all of a sudden you are in non-elastic range, and then you never come back in your hysteresis curve to 0. So this can also be calculated for atmospheric boundary layer winds, which they did. This is just to demonstrate that atmospheric boundary layer winds are quite often more nasty than downburst winds. Strong atmospheric boundary layer winds result in more nonlinearities, as you can see, as some cases of downburst winds. So it's not always the downburst is the worst of everything. But here is another very interesting analysis. This is interstory drift ratio. So what is that? So that is how each story is shifted compared to the other story and then normalized by the height of the story. And you can see that story number 10 has the largest interstory drift ratio, the largest displacement. But as I said, this gets profoundly different. I didn't present here for shortness. If you take atmospheric boundary layer winds, then the top story, or towards the top, you have the biggest responses. By the way, these gray lines are different realizations from our Monte Carlo simulations. That's why we couldn't run finite element models for everything. And the red is average. You can also see what somebody asked in my first talk. You can see just by eyes that this distribution of gray lines is not Gaussian. It's positively skewed. So again, the question is the red line the best representation of this whole response? But it is what it is. That's another topic. And here is residual interstory drift ratio. So that's basically how much structure remembers of after nonlinear response. So you can see that it reaches almost 4%. So permanently you get deformation in this structure, whereas maximum instantaneously is about 6% or so. And here, I'll skip this for shortness, but it's basically ratio, well anyways, I'll skip it for shortness. If I said right, it defeats the purpose. But here is the ratio, well, this is basically maximum ductility that you need for to design building for demand. And here is parametric study. So we changed, you remember that profile, nose profile with, well, they changed the height. I didn't do anything here. I don't even know why I'm presenting this. But anyway, here is the change. I'm just honest. I participated in an additional idea of the study. But, they changed the height of the maximum velocity in downburst outflow. And you can see, this is very interesting. It can have profound influence on the response, again, expressed as interstory drift ratio. So we can see this red is when the maximum outflow is at 30 meters above ground, and this is not uncharacteristic. The mean peak, on average, the height of the maximum velocity is between 80 and 150 meters above ground. But 30 is not something unheard of. And this is, so in atmospheric sciences, we know that as the density difference between downdraft and the ambient air, as the density difference increases, this nose decreases. So potentially, if we have downdrafts that are very strong and that are very dense compared to ambient air, it is more likely to have peak closer to the ground than in other cases. And yeah, these are different, mean ductility, residual, and ISDR, okay? And another, this is the last basically slide of info results, is that if we change modulation factor, so as I said, basically turbulence density, because turbulence intensity is modulated by mean wind speed and it's uniformly modulated. That's also been demonstrated, for example, by Roncallo and Solari, that turbulence is uniformly modulated process in this case. So if we have basically laminar flow, or very weakly turbulent flow, then the responses are much smaller, again in terms of interstory drift ratio. But if we have very turbulent flow, then the responses are much higher. And you can see, depending on the turbulence intensity, you get actually different dependence on height, which is also very interesting. So what are the conclusions? Well, nonlinear dynamics matters in this case, particularly what we are now continuing to research in another study, the consequences, significant damage accumulation was observed over 3% in case of these parameters that we varied. Parametric studies in this case are very important. Turbulence is very important, and what we concluded is basically that we should do more of this, and we are doing more of these and similar studies, okay? Thank you very much.